Okay, this is the second hour of Physics 1C for September the 8th, and we're continuing to discuss the definition of what an electric field is, and now we are trying to finish this problem up. So before the break, we found what the electric field was. It's this long number right here. That's just the electric field at one location, this point P right here. And for part B, we want to find the force on a charge. If we were to place a charge, Q1 equal to 2 microcoulombs at point P, what would the force be? Let me take our picture. Let's put it down here. Now, if I take a charge, let's scroll back up and see what the value was. It was Q1 equal to 2 microcoulombs. So let's take a charge. Let's place it right here. I could have sworn that I selected this, but it didn't select it. Click. There we go. So if I place a charge right here, and I tell you that that charge, Q1, is equal to 2 microcoulombs, we now want to find the force. It is a positive 2 microcoulomb charge, so we know the force should point up and to the right. According to our equation, all we need to do is to take that charge, Q1, and multiply by the electric field that we found already in part A. So let's do it. So we take the force, and we say that, or so we take the charge Q1, so it's 2 microcoulombs. So you put 2 times 10 to the negative 6 coulombs, and then we just multiply that by, I'm going to write this in a little different way. I'm just going to put all the exponents out here, times 10 to the 7 newtons per coulomb, makes it a little easier. And I will try, I'm not going to do that for now. So our answer then is going to be, you can see 10 to the negative 6 times 10 to the negative 7, we're going to get just positive 10. Oh, so we can actually do this without actually, I don't need to use the calculator because it's 2 times 2.4, which is 4.8, plus 2 times 1.2, which is 2.4. And Johnny, I heard you talking there for a second, so maybe it's working, I don't know. This is times j hat, and it's times 10, because it's 10 to the negative 6 and 10 to the 7. So 10 to the 7, 10 to the negative 6, that becomes 10. So actually, this is just going to be 4.8 times 10, which is 48. And 2.4 times 10, which is 24. And that's our answer, and it's going to be in newtons because the coulombs and the coulombs cancel right here. So that would be the force. And as expected, it points in the first quadrant because these are both positive, right? That means the force also points along this same line right here. That's the direction of the force on this particle. Does it make sense? Well, it's a positive charge, and it's feeling a force pushing it away from the positive charge. So that's correct, right? If it's still not loading, Johnny, you might need to restart your computer. Now you had to switch to your phone. I'm sorry to hear that. Okay, so...
Professor, I had a question.
Yeah, go ahead.
If we had multiplied the charge by the magnitude of the electric field,
yes,
would that have been an okay answer, or would it have to be in component form?
Well, I mean, you have different ways of writing answers in it. That would give you the magnitude of the force, right? So if I just take 2, or where is it? Sorry. If I take 2 microcoulombs and I multiply by this, that gives me the magnitude of the force. And that's something we can calculate as well, right? The magnitude of the force then, right, would be equal to Q times the magnitude of the electric field. And you'd also have to do this just in case because, yeah. So this would be something like 5.4, right, times 10 to the 7 newtons. But that would just be the magnitude. You understand that, right, Mendoza?
Yeah, I do.
Okay. Now, if you want to find the direction, you could write it as an angle, if you want to, right? You could figure out what the angle is down here, like this angle, right? By doing like an arctan thing, right? Arctan of 24 over 48 will give you the angle. So there's different ways to write this stuff. I think your homework is going to have a lot of questions where they ask for this. It'll also have questions where they ask for this, and sometimes they might ask for the angle. So you need to know how to do all of them. Do I care if you use that for vector notation? I mean, this is physics, so you should probably use this. Will I understand what you're doing? Absolutely. Will I like it? I guess probably not. But that doesn't mean I'm going to take off points for it. You can use that notation, Josh, but don't forget that there's still units in physics. You know what I mean? This isn't a math class. You still have units you have to put in there. So if you're going to do that, you have to include the units, right? So like this, I don't know how you would... I'm not going to go into details. We have a lot to cover today, but it's fine. I will understand what you're doing. Just be sure that you include the units as well. Okay, very quickly, part C was what would happen if I place... Oh, did I make both of them positive? Well, we're going to make one of them negative. I thought I made one of them negative. We're going to make Q2 negative. It's negative 5 microcoulombs. And the process is almost exactly the same. You just take F, we'll call it F2, is equal to Q2 multiplied by the electric fields. You put the charge in, you leave the sign on it, so if it's negative 5 microcoulombs, that's negative 5 times 10 to the negative 6 coulombs, and then we multiply by the E field again. Someone's queuing their mic, and you need to fix it. I think it's you, Johnny. It's probably because of your phone. You might want to mute your mic on your phone. I think it looks like you fixed it, though. We multiply this times the electric field, which was here. We'll just copy-paste it from here. Come on, let me click. So we got that, and then we figure out our answer, and our answer is now going to be 5 times 2.4. Can I do that on my head? I don't know. It's 108? No. This one's going to be 120, negative 120 I hat, minus 5 times 1.2, I think I can do. That's 60. And that's going to be J hat, all in newtons per coulomb. All right, so for this one, when I take the same setup and we placed a negative charge in this location, so Q2 was placed right here, according to this definition, it says that the force is going to be back this way. And it worked out perfectly. But the force on the positive charge pointed away, and the force on the negative charge points back this way. You're absolutely right. The answer will be in just newtons. That is a mistake. I'm going a little too fast here because I want to move on. So that is the electric field defined in very simple scenarios. Does anybody have any questions? And thank you, Raina, for catching that. Electric field and electric force. Do you feel like you kind of understand the basic idea before we start to do things that are a little more complicated? So just to reiterate, let's go back through what we did today. The definition of the electric field for a point charge is this right here. We figured that out because we defined the field by taking force and dividing by charge. So basically, when you compare the electric force between 2 point charges to the electric field, there is only one thing that's really different. And that's that the electric field has one less charge. Because the electric field is produced by a single charge. Every single charge will produce its own electric field. So what happens when you have multiple charges? Well, you get 2 different electric field vectors, and you can add them together. So that's the next thing we're going to do. One thing I will say, just try your best to pay attention for the rest of today's class, because it is about to get really challenging. Not this problem, but the next problem will be very, very challenging. Okay? So if there's anything you don't understand about the problem we're about to do, if there's anything I do that you don't understand, please, please, please ask right now, because it's about to get really hard. You're about to see why it is that people think Physics 1C is such a difficult class in the next hour or so. Alrighty, so now we're going to look at the electric field created by a dipole. And much like superposition of forces, when I want to find the electric field created at one location, I can add up individual electric fields created by other things, and that will tell me what the total electric field is, just like adding up forces. You can add vectors anytime you want to, and if I have multiple objects, I can add up all the electric fields created by individual objects, and that will give me the total electric field. Alright, so here's a question that's from your textbook. Do you need me to make the... Do I need to make it bigger, or can you read this okay? Make it just a little bigger. Can you all read the words? I guess it depends on how big your screen is. Hopefully you can read it. The field of an electric dipole. You all have heard the term dipole before, right? You may have heard, I know that because people talked about it last time, that water is a polar molecule. Yeah, you heard about it in chemistry, right? Dipoles are a pretty important thing in chemistry. Well, they're also an important thing in physics. And, in chemistry, it's because most molecules, most atoms have this dipole thing that you can measure, and they become important. And we'll talk about that more here in a little bit. All right, so we have point charges of positive 12 nanocoulombs and negative 12 nanocoulombs that are 0.1 meters apart. So here and here, right? And because they are equal and opposite, that's what makes it a dipole, okay? Positive charge, negative charge, same exact value, that's what makes it a dipole. All right. They are 0.1 meters apart. So the distance between them is 0.1 meters, and you can see that that's broken into 6 centimeters and 4 centimeters with this point A right here. Such pairs of point charges with equal magnitude are called dipoles. We want to compute the electric field caused by Q1, the electric field caused by Q2, and the total field at point A, point B, and point C. So point A is right here, point B is right here. These two are going to be very, very simple, and then point C is up here, which is going to be a little trickier. Although it's still not that hard. So let's go about doing that. Notice there's 9 things that you have to calculate in this problem, because we want to find the electric field caused by Q1, the electric field caused by Q2, and the total field. So 3 different things: the field caused by Q1, the field caused by Q2, and the net field at this point. That's the first thing that we want to do. So we'll start off by doing part A. I think what I'm going to do is I'm going to show you how to do part A. I'm going to let you do part B, and then I'll kind of set up C, and I'll let you do that one as well. Hopefully we can get this all done in a reasonable amount of time so we can go on to the next stuff. So, part A. Does anyone... Do you all need more time to think about the problem before I even start doing anything? Maybe you do. Let me give you 30 seconds or so. Read the problem, maybe draw a sketch. Think about it. Okay, let's look at point A. So, at point A, the first thing we're going to want to figure out is the electric field created by Q1. I'm going to call this E1, and we're going to put a little A down here to represent that it's at point A. We're going to have a lot of subscripts, so just kind of bear with me. Now, first thing to do when you're thinking about electric fields is remember that it's a vector, and that means you better draw a picture of it. So, if I come to the point A right here, right, and I think about Q1, what's the direction of the electric field created at point A due to Q1? Just Q1. Should I draw a line? This way, or something else? Is it to the left? Is it to the right? Okay, it's to the right. That's correct. And we'll just draw it maybe like this big. Things are going to get pretty cluttered in our diagram here. All right, so that's E1A, right? And it's a vector, yeah? What's it equal to? Well, we have an x and y direction here, right? So this is going to be your I hat direction. This is going to be your j hat direction, right? So I would say, if we want to calculate what that is, well, we have some information, we might as well write it down. Q1 is positive 12 times 10 to the negative 9 coulomb. Q2 is negative 12 times 10 to the negative 9 coulomb. So And the other piece of information that we're going to need, the only other thing I think, is the definition of the electric field of a point charge. So when you have a point charge, this is your electric field, and in order to turn it into a vector, you multiply by r hat. Okay. So I would argue that for E1A here, all we have to do is just put in k. Dang it. Okay. All we have to put in here is just k multiplied by q1 divided by r squared. And then if we want to get the vector, we need to put an r hat in here. Okay. This should be pretty easy for us here, though. So what's the value of r in this case? What's little r going to be? 4 centimeters, right? So little r is equal to, r is equal to 0.04 meters. Okay. All right. And for r hat, what's r hat going to be equal to? Well, it might help to define r to be equal to, in terms of a vector, 0.04 meters times I hat, and then r hat is just going to be I hat, right? Why is it 4? Well, the definition of r in this equation is you go to the point and you look at the distance. Oh, it's, yeah, 4 is wrong. 4 is not the right answer. It's 0.06. I'm so sorry. It's 0.06. Yeah, I'm being lazy. In this equation, it's the distance from the charge q1 to the point A, so this is our r right here. That's r. I'm so sorry. So this should have been right here and here. These should be 6s. So sorry. I'm like looking at chat and not really thinking, so I'm glad you all catch that. Good job. So r hat is I hat, though. That's the other piece of it, right? R hat is basically just I hat. Okay, so that means we plug everything in. We have E1A. This is equal to k is 9 times 10 to the 9. Q1 is 12 times 10 to the negative 9. Nanocoulombs is kind of nice because this will cancel out with that. And then we have to divide by, we'll throw an I hat in here because we said R hat was equal to I hat. And we divide this by R, which is 0.06 meters. And then we square it. So E1A is going to be equal to 108 divided by 0.0036. Actually, that would be like 12 over 4, which is 3. So it's going to be something 3. Let's see. 9 times 12. I sure do. Oh my god, I'm so sorry. You know, I'm always going to make mistakes, but I will say that it's really difficult to lecture for 6 consecutive hours, and I had 3 hours of lecture right before this class with a 10-minute break. It's hard to keep your mind straight, so I apologize. I'm much more likely to make mistakes, so thanks for keeping me on top of my toes. All right, what do we get here? 9 times 12 divided by 0.06 twice. It is 3 times something. It's 30,000. And the units for this should be newtons per coulomb, and it will be times I hat. Does anyone have any questions about that? Alrighty. I'm going to wait a moment for questions. Well, someone's typing, but we'll just let that go for a second. Next part was compute the electric field caused by Q1, also caused by Q2. Well, now we have to look at Q2, and we ask, at point A, what is the direction of the electric field created by Q2? Is it left? Is it right? Those are the only options. What do you think, left or right? The electric field created by, yeah. I only briefly mentioned this, and I probably should have put more emphasis on it, but when you have a negative charge, the electric field points towards negative charges, and it points away from positive charges. So we'll call this one E1B, and it points to the right. Can I only calculate for magnitude and then add it to a lecture like I studied? Yes, you can. You can do that, definitely. It will also work, Ton. You can try it yourself. I feel like it's a dumb question, but how come vector r and r hat are the same? They're not. They're not. It looks like they're the same, but this one has an I hat. You see that? R is the vector that has the magnitude and direction. This one is just 0.06. Alrighty. For E1b, I might do this one a little more quickly. For E1b now, this one is equal to k times the charge. Can I just plug in the numbers? So it's going to be 9 times 10 to the 9. We're going to multiply that by the charge. The charge is negative 12. And what's the distance here? Let's figure this out. For B, what do we have? I really should have. Okay, what is R magnitude equal to for B? What's the magnitude of R going to be for Q2? Oh my god, I'm using... Okay, this is just getting really bad. I gotta fix all this stuff. This is not E1B. No. We're not... This is charge 2, right? So we're gonna call it E2A. E2... Whoops. This one's E1A. But this is gonna be E2A. Oh my god, it's so bad. 0.04 meters, absolutely. So for B, we're gonna use 0.04. How would I write R then? Is it going to be 0.04 I hat? Should it be negative 0.04 I hat? What should it be? Positive? Okay, I'm going to go back to the definition because this is something everyone's going to get confused by, and it's going to happen multiple times in this problem. Where did I define R? There we go. Here we go. This is how you define R. You start from the charge, right? And you draw a line from the charge to the point. You guys understand? Remember this. Position vector is from the charge to the point, right? From the charge to the point. So the R vector in this case would go from the charge to the point back like this. So it's negative, right? So negative 0.04 meters, and then obviously I hat, right? Okay, so what is R hat now? Well, we just divide R over R, and we're going to get negative I hat, right? So we have negative I hat. That's the R hat. Then we just divide by the magnitude, which is 0.04. And we have to square that, of course. This gives us the answer for E2A. So it's the electric field created by charge 2 at point A. That's why we're using that notation. And this one's going to be 9 times 12, which is 108, divided by 16. I don't think 108 is commensurate with 16. So 108 divided by... And I got 67,500. Newtons per coulomb. Now, what happened with the signs? Well, it's a negative sign times a negative sign. It's really important to understand. If you are going to use this definition, right, you need to put in the charge like with a positive or negative sign. So I left the negative sign in there. But keep in mind that this can also be negative, right? R hat can be negative, which is what happened here. So we got a negative times a negative, which gave us a positive answer. And that is, in fact, the right answer. Did that make sense? In spite of my horrific mistakes that I made in these labeling. Did it make sense? If you say no, I would understand, because I felt like that was a horrible explanation. But anyway, I'm sure you'll all be nice. So if the blue is the blue vector at a pointing right, be left then? At A pointing. Is the blue vector at A pointing right, be left then? So this might be confusing. I'll get rid of that real quick. This is the vector right here. I'll pull it down. That's the vector from point A, and it points toward Q2. Yeah. I just love babbling to your tables. It's funny. Yeah. Did that answer your question, Brandon? Okay, good. Hard to see. I know. All right. in the interest of clarity, I think what we should do... No, it's positive. The answer is positive. And again, I'm gonna say this because I didn't really emphasize it, but if I have a positive charge, the electric field points away from positive charges. If in a separate region of space I have a negative charge, the electric field will point towards the negative charge. Okay? So in this case, the electric field points toward the negative charge, and it points away from the positive charge, so they both happen to point in the exact same direction in this part. What's negative? No, nothing's negative in part A. The R hat is negative in the case of Q2. All right, now, in the interest of keeping things neat, we're going to come down here, we're going to draw a new picture, and we'll do all the work on this same picture over here. I will continue with this stuff. Click that down here. All right. So, for part B now, we need to figure out the exact same stuff for part B, but I want you all to try to do this yourself. I'm not going to give you any guidance. I'm just going to let you try it. Maybe you fail, maybe you succeed. It does not matter. Just give it a try. Oh my god, we're going through time so quickly. I guess we're only 30 minutes in still. So now try part B. So at point B, you need to find, I want you to use the same labels as I used on the first part too. So you're going to have to find E1A. You're going to have to find, nope. It's going to be E1B, right? Yeah. You're going to find, we'll call it E1B. That'll be the electric field created by charge 1 at point B. We're going to find E2B, the electric field created by charge 2 at point B. And finally, we're going to find... Oh, we didn't do that for the first part. I'm sorry. Let's finish part A, because part A we also had to find... Not only do we need to find E1A and E2A, the electric field created by each of those, we also need to find the total field. We didn't do that. So the total field, we just have to add them up together. That's exactly right. So let's do that here. So we'll say E total is going to be equal to E1A plus E2A. And because everything is already written in vector form, all we have to do is just add the two things. So that is 30,000 plus 67,500. They are both multiplied by I hat. They're both in newtons per coulomb. Oh yeah, this is missing an I hat. You're right. This should have an I hat here too because I wrote it as a vector. They both have I hats because it came from, that was at the end. I left that off. Sorry about that. There should have been an I hat right there. I fixed that. So then we get an answer of 97,000, right? So then E total is 97,500. It's per coulomb. Yeah. Alrighty, so that's the answer to the first part. Can I explain for E2A why R hat is negative? Brian, it was... Yeah, sure. So let me come down. Okay. So let's... So I have this negative charge that's right here, right? And we're at point A. And I'm supposed to figure out, as you're asking, why is R hat negative, right? So the first thing to do is just to draw R. How do you draw R? You draw R by drawing a line from the charge. You draw a line from the charge to the point. Charge to point. Just remember that. Going from the charge to the point. And that is your vector. Does that make sense, Brian? You draw a line from the charge to the point. Okay, great. Now, I want you all to try part B. So in order to do that, you're going to need to do three things. You need to draw a vector for E1B at this point. Does it point left? Does it point right? I don't know. Think about it. You're going to have to draw a vector for the electric field created by Q2. Again, you're going to have to think, does it point right? Does it point left? Remember, electric fields point away from positives and towards negatives. Hopefully that'll help you. And after you've done that, you'll calculate E1B, you'll calculate E2B, and you'll calculate the net field as a result, okay? So I want you all to give it a try. I'll give you like 5 minutes. I know that's not much time, but we gotta keep going. One more minute. Yes, Brandon. Ricky, I just got an email back. I'm only going to be able to add one person. So I'm going to say no. Yeah, that's right. I'm so sorry. Okay, let's continue. Yeah, he did respond. He said it's a problem. There's 15 setups. There's nothing I can do. I can only have one person. Okay, so field of an electric dipole. We are looking at finding E1b and E2b. So let's go here on our diagram and let's draw a picture of what the directions of those vectors are going to be. So we'll use the vector color of red for E1a, or sorry, for E1b. What's the direction of the electric field vector at point B for this charge Q1? Does it go left? Does it go right? Do I draw a vector this way toward it? Do I draw one to the left? That's right. Electric field vectors for positive charges, they always point away. So we'll go ahead and label that one. That's going to be what we call E1 at point B. All right, for the negative charge, I'm going to draw a vector in here for that one. What's the direction of the electric field due to the negative charge at point B? This one's going to go to the right. Because again, if you don't remember, as someone pointed out in the chat, if I were to place a positive test charge right here, and I didn't worry about this one, it would be attracted to the negative charge. So we draw a line like this. Now in this case, they have exactly the same size. They are the same size, but opposite signs. So since charge 2 is farther away, I'm going to draw this vector smaller. Charge 1 is closer, and the electric field is inversely proportional to distance, so E1 should be bigger, and I did it again. This should be E2b, not E1b. This should be E2b. This is the electric field created by charge 2 at point B. All right, now we want to calculate what they are. Let's do E1b first. So, what we had to do previously, we had to calculate what all the individual pieces of information are. So, let's start off with the length r. How long is the length r from here to here? You can see on the picture it's 0.04 meters. Now, how do we draw our r vector though? Remember, we have to draw a line that goes from the charge, right, to the point, from the charge to the point. That's what the r vector is going to be, right? It's going to go from the charge to the point. So what should I write down for that? Negative I hat. So we're going to write negative 0.04 meters multiplied by I hat, which then means that r, which to remind you, you get by taking r and dividing by r, the vector divided by the scalar, this will give you negative I hat. Okay, so we've got r hat, we've got r, we obviously know what q is, and that's all we need. So, E1b, let's put this all in red. So E1b then should be equal to, you switch it to red, but then it doesn't stay red. Okay, E1b is going to be k, which is 9 times 10 to the 9. Multiplied by q, which is positive 12 nanocoulombs, times r hat, negative I hat. Divide by r. What did you all get when you did this calculation? Certainly some people got the answer. What did you get? Did you get like negative 67,000? Yes, you did. Negative 67500 newtons per coulomb times I hat. Alrighty. What about E2b? For E2b, we'll do this one over here. What do we know? Well, we know that r is equal to, oh, it's squared. So sorry, that is squared. Thank you. That's supposed to be squared right there. Thank you. Okay. What do we know about E2b? Let's do it same order as before. What is R equal to in this case? What is R going to be? Well, R is the distance from point B to here. That's R, right? What is it? What's it equal to? The distance from Q2 to point B is 0.14 meters. That's right. What is R vector? Is the R vector going to be positive or negative? Well, how do we do it? We draw from the charge to the point, so it will be negative again. Because you're going from here to there. That's your R vector. It's going to be negative, so it's going to be negative 0.14 meters times I hat, which means that R hat is also going to be negative I hat again. So plugging everything in together now for E2B, we're going to get that E2B is going to be equal to K. Multiplied by the charge, which is negative 12 times 10 to the negative 9 coulombs. Kind of running out of room here. We're going to shut this down. There. We need to multiply that times R hat, which is negative I hat. We need to divide that by R squared, so divide by 0.14 meters, and then square it. And what did you all get for this answer for E2B? 5510. That seems reasonable to me. Did anybody else get the same answer? And notice negative, negative, we're going to get a positive I hat out of this. Same thing. Okay. I'm just going to trust you all. This is 108 divided by 14 squared. 14 squared is, I don't even know. But I bet you all are right. I'm just going to just do that part of the calculation, and we will see just real quick. 108 divided by 5510. I agree. Okay. So those are our answers, and of course that's not the final answer. We also need to find, what did it say? Electric field caused by Q1, the field caused by Q2. We got those two there, right? And the total field. So this is part B we're doing here. The total field will be E1B plus E2B. I noticed that I dropped my vector symbol. Apologies for that. That is a vector. That's a vector as well. These are vectors. So you just add them together. I'm just gonna add them together in my calculator. So I'm just gonna go 5510 minus 67500, and I get negative 61, about negative 62,000. So you get negative 62,000 newtons per coulomb times I hat. And the net field does point left, which is what we expect because Q1 is closer. So that means E1B has to be bigger than E2B. And it is. You can see, E1B is more than 10 times as big as E2B, even though they have the same charge because of the distance between them. All right. Any questions about that? All right, we're going to go for about another 8 minutes and solve this last part. We have quite a bit of material still to cover, so for this last part, I'm just going to show you how to do it. Largely because no major things are going to change, and I very, very much want to get on to what's left to do in today's class. We're going to make this a little bigger for this part. Okay, now this one's a little trickier, because at point C, we are now no longer along a straight line. You notice in the previous parts that everything was in terms of I hat. That's all going to change in this part. And probably the way that I do it will also change a little bit, mostly because I want to show you multiple ways to do things, and because I think this way is going to be a little simpler. So, if I come to point C, and I ask, what is the direction of the electric field created by Q1 at point C? Don't worry about Q2, just ignore it. Just thinking about Q1, what's the direction of the electric field here? Is it going to go up this way? Is it going to go down this way? What's it going to be? Up this way, down to the left, northeast, upwards. Okay, so it's going to go away from Q1. Again, if you don't remember that, it's because it's a positive charge that it works like that, and we will make this one red. Okay, that's going to be... I'm not going to use the symbol E1C this time. I'm just going to call this one E1 just to keep things simple. Okay, I don't want to put extra symbols on here. There's going to be a lot of extra stuff going on here. So we're just going to call that one E1. Okay? What about E2? Should the direction for the electric field for E2 point away from Q2 or towards Q2? And again, if you don't remember how to answer that, you say, what would happen if I put a positive test charge right here? Would it be attracted to Q2, or would it be pushed away? And the answer is it would be attracted. So we're going to draw a vector. This vector is going to have exactly the same length. Now, I don't know if it exactly has the same length, but I'm going to try to draw it in such a way that it appears to have exactly the same length. So E2 goes down this way, and E1 goes up this way. They should have the same size because both Q1 and Q2 have the same magnitude, and Q1 is a distance of 13 centimeters away from point C. Q2 is the same distance, so the value of the electric field vector, right, will be the same for both of them, right? Because Q is the same, and R is the same, and K is the same for everything. So the size of these are the same, okay? The magnitude, right? Do you all agree with that from the setup of the problem? That the magnitude of these vectors would have to be the same? Okay. So we really only have to calculate the magnitude for one of them. So let's do that real quick, because we know they're the same, right? So let's just do magnitude to mix up the way we're doing these problems, because I think as Tom Bui mentioned earlier, she was saying she doesn't really like the unit vector stuff. So let's do this without using unit vectors. And then I'll talk about what you would do with unit vectors. Okay, so E1 is equal to K times Q1 divided by R squared. What is R going to be equal to? R is going to be the distance from the positive charge to point C. In this case, that distance is along this line, which is 13 centimeters, or 0.14 meters. Oh my god. 0.14 meters. So, plugging everyone in together here, we're going to get the magnitude of E1 is going to be 9 times 10 to the 9. Multiplied by Q1, which was 12 nanocoulombs, so 12 times 10 to the negative 9 coulombs. If you're confused what I'm doing here and how it's different, notice I'm just finding magnitude now. We're not finding direction, and the reason is because they're going to have the same magnitude. R is 0.14, so we're going to do 0.14 meters, and then we're going to square it. Oh, 0.13. What's wrong with me? There's 0.14 in the last one. It is 0.13. You all are absolutely right. I'm sorry. Okay. 0.13. There we go. So what's that equal to? That is going to be 108 divided by 0.13. Oh, did I do that thing again with the C? Oh, okay, I'll fix that too. So I got 6390. Right here, kilograms squared. It should be coulomb squared. It's so similar to the gravity equation, that's why I always confuse that. I got 6391, let's call it. We'll call it 6390. Do you all get the same answer? Give you a second. Okay. And then, as we said, this is just the magnitude, but it happens to be the magnitude for both of them. In fact, maybe we just call it E if we want to, but I'm not going to do that. We'll call them two different things. All right. Now I want to add these vectors together, because after all, the net vector, the total vector that we're going to want to get here, should be equal to E1 plus E2. But now we can't just add them like we did in the previous part. In the previous part, we wrote everything into vector notation and then we did the addition, but everything was pointing only in the x direction, so it was super easy to do it. So what do we need to do now if I want to add these two vectors together? There's multiple answers, I guess, that are right, but all of them involve, in some way, breaking these vectors up into components, right? And then summing the components? Yeah, components. That's everyone saying the right thing. So let's go about doing that. So for vector E1, we can break it up into a component that points this way. We'll call that one E1x. And we can drop another component that's going to point up this... Oh, no. Oh, no. Why does Control-Z not work? But this works. Oh, that's also not working. Okay. Okay. Click on this, click on this, click on this. Okay. Then we're going to go a vector to go up from here up to here. So that allows us to break this one into components. Come on, click. Click. What's it doing? Oh, then it stops? Alright, really? Okay, is this real? Is this actually happening? Click. Click, just stop. What do I need to do? Seriously? I can't even click it now? Come on. It's stuck on this thing? Is that what's going on? Okay, I apologize. Getting a little tilted by OneNote here. Boom, we got it. I don't know what the difference I did there was. Okay. Will they share the same components? Yes, they will have the same components. So this is going to be E1x, and this is going to be E1y, and we will find out what they are. I'm probably going to have to move this one down a little bit so I can draw an angle in there. I'm going to use the angle method, so we're going to calculate what this angle right here is, theta. And then we're just going to say that E1y is going to be equal to E1 times the sine of theta, because it's opposite this angle. And we're going to say E1x is going to be equal to E1 times the cosine of theta. So we need to find out what theta is. How do we find out what theta is? Well, theta has already been found. It is about 67 degrees, you're saying, right? Okay. And I'm guessing the way you found that was the triangle. Since this side down here is 10 centimeters, that means that this side right here is 5 centimeters. If I drop a perpendicular bisector, which means that I can find the angle alpha. Oh, there's already an angle. Let's use alpha. We'll just use alpha. We'll call it alpha. That's even better. I forgot that there was an angle on the picture. Alrighty, so we got alpha right here. We'll call it alpha. So if I do this, if I draw a line straight down from here, I'll make a right triangle. That right triangle will happen to have sides that are 5 centimeters and 13 centimeters. And if you take 13 squared, which is 169, you take 5 squared, which is 25, and you do 169 minus 25, you're getting 144. Take the square root of that, you're going to get 12. Because this is a 5, 12, 13 triangle. And then you can use any of these sides if you want to figure out what alpha is. I'm assuming that you did something like alpha is equal to the arc sine of 5 over 13. That should work, and you're going to get that alpha then is equal to... Is this what you did, Ton? Something like that? It's arc cosine. You're right, it's arc cosine. Sometimes I'll be saying something, and I, like, as I'm saying it, I'm not really thinking about it, but I just want to say something to keep going, to keep the flow, which is bad. I shouldn't do that. So arc cosine, 5 over 13. You could also use arctan of 12 over 5 if you wanted to. You get 67 degrees. So that's alpha. And now that we know what alpha is, we can find E1y and we can find E1x. I'm just going to go ahead and say that we can also find E2y and E2x in the same way. They're going to be a little bit different. So E2y is going to be negative E2 times the sine of alpha. And E2x is going to be positive E2 times the cosine of alpha. Why is E2 going to have a negative sign? E2y going to have a negative sign in front of it? Well, because it goes down and to the right, which means that if I were to draw a vector to represent E2y, it would go down like this. And if this is E2y, then you can see that it's pointing down and it's negative. In addition, one other thing you might notice here is because they have the same sign, or the same size, E1y, which is up, and E2y, which is down, are going to exactly cancel out with each other, right? When we add these things up. And you can see that here. So going on to the next step, what I want to do is I'm going to sum up all the components in the y direction, which means I'm going to take E1y plus E2y, but that's just going to be like doing E1 sine alpha minus E2 sine alpha, but E1 equals E2. So the sum of the electric field vectors in the y direction is equal to 0. That's the y component, 0. We need to do the same thing in the x direction. We'll sum up all the vectors in the x direction. Notice this is really similar to stuff you probably did in Physics 1a. And this is going to be E1x plus E2x. But you can see them both there. E1x is E1 times the cosine of alpha plus E2 cos alpha. But E1 is equal to E2. So that means this is going to be 2 times E1 cosine alpha. This is going to be the x component. So then EX is going to be equal to 2 times E1, which we calculated up here was 6390. And then we multiply by the cosine of alpha. And cosine of alpha, well, I can tell you right now, the cosine of alpha is 5 over 13. Right? You think this way is easier and less make mistakes because I don't need to care about r hat? Yeah, I agree. 100% agree, Tomboy. But I like to show things different ways because there's actually a lot of people that would much prefer to do it this r hat method. And I'll show you how to do that here in a second. But you see what I mean? It just really just depends on what you're comfortable with. And for you, this method is easier. It's also easier for me because this is how I learned it, but that doesn't mean it's going to be easier for everyone. By the way, cosine of alpha is equal to 5 over 13. Hopefully you can see that in the picture here. This is a 5, this is a 13, this is alpha. So the cosine of the adjacent over the hypotenuse will also be 5 over 13. That's why I put that in right there. And so we're going to get 10 divided by 13 times 6390. And I get 4915 newtons per coulomb. And then now we basically say, turn that into a vector, and we say the net electric field, or the total electric field is going to be equal to 4915 newtons per coulomb. This is the part about this hard, though. I now have to turn this into a vector. Luckily, this one's going to be easy, because the net vector now, at that point, is going to point directly to the right, right? Because E1x was pointing to the right, E2x was also pointing in that exact same direction, right? So you add them up, and you get that the net electric field at this point, which is at along kind of a bisector right here, points to the right. In fact, if you were to come to any point along this line, you would find that the net electric field always points to the right, anywhere along this line. Okay, does anyone have any questions about what we just did? Do you want to talk about how you would do it if we used the r hat method? Might as well. I mean, we don't really have time to do that, but that wouldn't hurt. So if you want to use the E2b got a little confusing with the negative for some reason. Oh, in the first two parts? Maybe. Yeah, I understand. Let's just talk about what we would do for r hat here. If I want to find, you know, if we want to do this the other method, what we would do is we'd say, okay, well, we know E1 is equal to k q1 over r squared times r hat. And so just as we did before, we need to find what r is. So I would say in this particular case that r is going to be a line that's drawn along this, right? It goes from the charge up to here. That's going to be your r. And in this case, I would say that it is 5i hat plus 12j hat centimeters. Okay. And then your r vector, you would have to divide this by r, which is this. Your r vector is going to be 5 over 13 I hat plus 12 over 13 j hat. That's your r hat vector, right? And then, you know, plug it all in here and see if you get the same answer. You will get the same answer. Absolutely will get the same answer. I promise you. Yeah, you can use whatever method you want. Whatever method you want. So feel free to try this out yourself. I promise you will get the same answer. Notice this 5 over 13 that shows up here also shows up here. So at the end of the day, no matter which method you're doing exactly the same thing. You're doing exactly the same thing. Should you change it to centimeters, simplify it? No. You don't want to leave it in centimeters. You have to convert to meters. You need to convert to meters. You have to convert to meters, always. Unless you're doing a ratio. Anyway, so there's your r hat. And we already know what this is, right? So we can even go ahead and say that if I want to write this down, what I'm going to get is that E1 is going to be equal to kq over r squared was 6390, right? So this is going to be 6390 newtons per coulomb, okay, multiplied by 5 over 13 I hat plus 12 over 13 j hat, right? And then E2 will be exactly the same thing with the minus sign on the j hat. That's E2. And then look what happens if you sum these up. It's really obvious. You can see how they cancel out, right? The sum would be, you would just add like this. It wouldn't be 0.05 over 0.13. Well, 0.05 over 0.13 is the same thing as 5 over 13. It's the same thing, Ange. You can put in your calculator and check. Yeah. Yeah, so then if you want to sum them up, you would get that E net, right, would just be equal to 6390 plus 6390, right? So it's going to be 2 times 6390 newtons per coulomb multiplied by 5 over 13. And look, it's exactly the same answer, right? So you end up getting E net, oh, whoops, vector symbol, I hat. You end up getting that E net, again, is equal to 4915. So, you know, which way is simpler for you? I don't really know. You just choose one, but at the end of the day, you're literally doing exactly the same thing. Either you're turning the vectors, right? These are actually vectors. You're turning the vectors into this vector notation, which basically just takes components and writes them as the x component plus the y component, right? Or you just split up the work and you find individually what each of those are, and then you come back in and you add the x components, you add the y components. I mean, it's no different. It's literally the exact same process. And you can see that you even get the exact same expression as long as you're careful enough to plug everything in right. So it's really up to you. You're definitely going to see a problem like this on your first exam. It will probably be harder than this. You'll see problems that are a little bit harder than this on your homework as well. So get used to finding electric fields due to multiple point charges, because we can make this problem even harder by adding more charges, basically, right? So if I added a third charge, like right here, for example, or like right here in the middle, and did all the same calculations, it would be quite a bit more challenging. The moment you add a third charge, you know, it's going to be quite challenging. I think this is already pretty challenging, even though the answers are pretty simple. So we need to take a break. Does anyone have any questions before we do so? We're going to have to take a shorter break because there's been so many things that have been kind of distracting us in this class. So we're going to take a 6-minute break. It's probably the last time that I'm going to do this semester, but or at least I hope it is. We're going to take a break till 3:47. That's not going to leave us. It's only going to leave us like 30 minutes left in the class. Will we ever use the z-axis? Possibly. Yeah. Possibly. All right, let's take a break.